Okay, so now give me a big number.
Like, how about what we were looking at yesterday, like 365 factorial?
365.
We don't know how many
Factorial.
digits this has.
Yeah, we don't know how many digits this has. But 365 factorial is 778. The log base 10 of it is 778.399. So how many digits does that
It
have?
is
Number has
779.
9 digits.
779
Wow.
digits.
It's a pretty long number.
Yeah.
That seems to be the number. And that would be hard to count, but we would just say it has 779 digits, which is an interesting fact all by itself. Now you give me another really large number.
What about one that's larger than 365?
Yeah,
Maybe 500 factorial.
500 factorial.
I wonder if it can take that.
Yeah. You have to go all the way up.
Clicked on the wrong thing.
This will be a...
It should be huge.
Whoa!
Alright, so there's a gigantic number, but a simpler way just to see it, or just to see.
It has 135
5.
digits.
1,135.
1,135 digits.
Yep.
So that's interesting. So that's a huge number.
Yeah.
But
I
are there
think I
numbers
wanna
that have
count
more
those.
digits than that?
Oh yeah, we could do like 10,000 factorial.
Okay.
I'm not sure if.
Well, let's move away from factorials now. What are some other large numbers that we know about, or other ways to write large numbers
Well,
other than factorials?
Like, how about scientific notation?
Okay.
Like 2 times 10 to the 18th or something.
Ooh, interesting. That's going to be a great example, even if I just keep.
I don't think I want to count that to make sure that's true.
Oh, I hope I was always moving these up high enough for them to be on the camera. All right, log base 10. You said what? 2 times 10 to the 18th?
Yep.
Yeah.
2 times...
D.
Is it the shift 8? Okay.
Let's see. I don't know how to enter 2 times 10 to the 18th, so let me. Oh, I got it. Okay. Let's scroll down to find the logarithm of that.
There.
Oh, sorry, I just missed it.
18.
2 times 10 to the 18. 18.301.
So that would
this-
have maybe 19.
19 digits.
19 digits. Now let's say, well, let's revisit log base 10 of 2. So that'd be 2 times 10 to the 0, right?
Yeah.
Okay. So remember, this one was 18.301.
This one is... It's around... It's 1 digit long because 10 to the 0 is 1.
So what is that number you see there? Here.
It's around 0.301.
Actually, let's memorize it to, like, more digits. 0.301, 0299. Okay. And now let's go back to 10 to the 18th.
301299.
3010299. Wait.
3010299.
Huh.
What?
Give me another power.
How about 10 to the 23rd? Well, it's
3010299.
And what's the number out in front?
And it's 23.
Okay. How about 2 times 10 to the 50th?
It'll... Well,
Seems like it's gonna be 50.
What?
50.3010299.
Huh. So we're stumbling on some interesting properties of this
power.
logarithm function.
Cool.
Okay. But maybe there's some other ways to get large numbers other than just writing other than scientific notation. What are some other ways we could get large numbers?
But 10 times, we could do the
We could
powers. Just,
Oh, powers. Like what? What's a big power?
do maybe like
how about 5 to the 32nd power?
Ooh, 5 to the 32nd power.
5 to the 32nd.
Okay, that's probably a pretty big number. We don't know much about it, but we can tell you from the logarithm.
0.000105.
Did it input it wrong? Oh, wait.
10 of.
I need an of. Yeah, that's good for noticing that was probably a mistake. There we go.
22.36.
22.36.
So it has 23 digits.
It's 23 digits. How about if we start looking at like how you get up to Graham's number? Maybe let's do powers of 3. Log base 10 of 3.
3 to...
That's 1 digit, right?
Yeah.
And then we could...
Sorry, I gotta reach around here. 3 to the 3.
3 to the 3. It's
1.43.
so
And then we just keep walking up the powers in the
Three.
tower, right? 3 to the 3.
yeah.
3 to the 3 to the 3.
Yep.
3 to the 3 to the 3. And we got
Already I'm up to 13 digits.
Wow.
3 digits. So. Wow. So it's around.
Look, just with 4 3s in a tower, look how many digits I have. It's 3 times 10 to the 12th. 3.6 times 10 to the 12th. So already 3 to the 3 to the 3 with only 4 powers of 3. That is the number of digits in that number.
Whoa. Oh.
So forget about how big that number is.
That's the number of digits.
Right. That's the biggest number we've seen so far.
Yeah.
That was bigger. Didn't we do 1,000 factorial?
Yeah.
Yeah. Wait, we did 500 factorial.
All right. So this is already bigger than 500 factorial by miles. Like, I don't even know if 1,000,000 factorial is that big.
Well, I'm not sure if Wolfram Alpha can do 1,000,000 factorial.
1, 2, 3, 4, 5, 6 factorial. Let's see if the number of digits is bigger than 3
times
times.
10 to the 12th.
No.
It's
The-
not.
There's
It's
a
5.
million. Here, this would be 10 million factorial.
How about 1,000,000,000 factorial?
10 million.
10 billion, 10 million factorial. No.
Still.
Still not.
100 million?
100 million factorial. No. 1,000,000,000 factorial.
Whoa.
We're still the digits is 10 to the 9th. We got to get to 10 to the 12th. 10 billion factorial.
10.
10 to the 10th. 100 billion factorial.
It'll be.
There now at least we're close, right?
Yeah.
Well, we need 3 times 10 to the 12th.
Right. We need 3 times 10 to the 12th. But when we're talking about the number of digits, at least now we're close. So what was this? 100 billion factorial.
Yeah.
100 billion factorial has, in the
Less-
same neighborhood of digits,
Yeah.
but fewer digits
Yeah.
than 3 to the 3 to the 3 to the 3.
Oh.
Would you have thought that?
No.
No.
No, not at all. So that's kind of interesting. All right, now you asked me about logs using other bases. All right,
Okay.
that gives me an opportunity to talk about what the logarithm actually is. Okay.
Alright.
Okay.